We're going to look at histograms next. And I do want to make a mention about the mean and medians. When you use a mean and when you use a median, you need to understand your goal. Sometimes books will say, well, use a mean if your data is somewhat symmetrical, use the median if your data is not symmetrical or some kind of, pushes to the left, to the right. In a minute, we're going to look at more language that'll help us make this more clear. It really is dependent on your goal. To represent, of course, the characteristics, maybe you would want to use the median or the mean, but it depends what you're going to use that information. So let's look at this concept called the histogram. The bar graph's probably one type of graph you're very familiar with. The histogram is, I think, underutilized. It is a wonderful graph I don't know why it's not used more often. What is a histogram? Well, a histogram is a graphical summary. I like to think of it that way. Okay. In my opinion, and again, as I mentioned, underutilized graph. It is used only for quantitative / numerical, not categorical. The concept, again, is just simple. Look at the data and create equal width ranges. What does that mean? Well, we're going to see in a minute. There are methods to determine how many ranges one should have, but we'll look at that at the end instead of use our intuition. We're not good. There's, again, methods just to figure out how many ranges, how many widths you need. And ranges are called class widths, or sometimes you see them as bin widths. Like Excel has this thing called bin width, but sometimes you see it again as class width. But in any case, in order to create a histogram, you need to make a predetermined choice of how wide to make these things. And the purpose of a histogram is to get an idea of how data is distributed by grouping the data into these intervals. I'm using a different word in case the other ones don't make sense. We created. You can think of a histogram as a visual, like I said, summary, which is an approximation to the population distribution. Think of, again, also, I'm going to use a different word. You can think of histogram as a visual statistic. It is a summary, but it's also like a statistic, which is an approximation to the population distribution, or again, where this one is the parameter. Not usually we use the word statistic to describe a histogram, but that's in reality what it is. It's some kind of way of condensing the information. It's a summary of the information, but a visual condensation. What does a histogram consist of? Well, let's say I have a bunch of data, right? So you have your data, and let's say that I have these numbers like 42, 43, 57, 44, 55, 71, 78, and so on, blah, 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 blah. So it's a bunch of data right here. So the idea is that you need to figure out how to group this information. But what we need to determine is how to create these little intervals, and then you count how many data fall into those intervals. So I'm going to make this very simple. So I'm going to go 40 here. So I'm going to make my class width, so my bin width, just 10 wide. So it's easier to keep track of. Okay, like so. And then on this axis goes the what's called frequency or count. So for example, up here 5 and then 10, 15, 20, things like that. So now what we do is we start counting, like how many fell into 40 and 50. And let's say, just to make quick, I'm counting, and say I counted 5. So then you would have a rectangle that would rise to 5. What suppose that between 50 and 60, there were 15. So over here to 15, I counted 15 that fall here. Again, making these numbers nicely lined up, but of course it could be 12, 13, whatever, but 15. Let's say between 60 and 70, there's nothing. And 71, 78, let's say it's another 10 right here. And then between 80 and 90, we count 7. So I'm just like somewhere between the two, 7 somewhere in there. And let's say that's all it is for the moment. So again, this axis contains, so now my class width is 10 units wide. I didn't just describe what the unit is here. Okay. And so, for example, if I look at rectangle 1, it says there are 5 data values. Between 40, and 50. Now, another thing you want to keep in mind, let's say that I have one data value and it's, let's say 80. Where does 80 go? Where does that 80 go? After all, 80 is right here, right at this cutoff point. So does 80 go, does it get counted for this rectangle or does it get counted for that rectangle? And the answer is it depends on what you want to do. But once you establish your rule, you need to be consistent throughout the entire data set. So we can have it so that using, again, algebra here, a little bit of algebra, this means include. So you can always include the lower number, but not the top number. So this means exclude, go up to that number and exclude it. Or you can work the other way around. Don't exclude the bottom number, but include the top number. Which one is it going to go? Typically, using software, this is the default. Always include the bottom, not the top. But you can, if you use software, sometimes it gives you a choice, like use this one instead, this rule. If we use this rule, which is include the bottom, but not the top, then 80 would be included here. That's where 80 would go. It would be counted in this part of this rectangle right here. If we use this rule, 80 would be counted here because it only the top goes to this region. And that's how you tell. Okay, what about between 60 and how many data values? In the interval, that's my back and use notation, 60 to 70. Don't include 60, but include 70. And the answer is 0, right? So the empty space just means there's no data values that fall in between this number and that. So that's how you read that. So you're not going to create a histogram by hand. You're going to use software. But if you did have to do it by hand, that's how you would do it. It'd be easy to order all this information and then just start counting how many fall in here, and then you raise your rectangle to that amount. How many fall between here and here? Raise your rectangle to the amount you count. And again, be aware that you need to use one of these two rules. And then once you establish one, maintain with that. Axis here is a frequency, a count. So again, really a frequency is the same thing as just counting. It counts. Okay. So again, 5, 10, 15 things, 20 things, and so on. Relative frequency is what? A proportion. Meaning 10% or 20% or so on. Obviously, you could think of it as a percentage if you're going to write percentages, but then you have to make sure you let the reader know by putting the appropriate symbol right here. But I could always turn this into a relative frequency by saying, okay, I have different values, like maybe it says 2%, this is 3%, sorry, 2% to 4%, 6%, and then you raise the rectangles to the amount. But then you have to count everything. You have to determine n, and to do a relative frequency for each one, you would have to figure out how many fall into, I'm going to call it count 1, and divide by n. Then you between here and here, how many fell into that count, and divide by n, and so on. And then here you would mark appropriately what proportion you're moving to. But again, in that case, remember, all these rectangles will need to add up to 100%, since the sum of C1, C2, and so on, different counts, at the end have to add up to n. Okay? But that's a relative frequency. Again, software will give you the choice. Do you want to just have this axis be a count, or would you like it to be instead a proportion? So again, maybe it'll say 10%, 15%, 20%, and it depends on your data, how big the highest rectangle is. So that's how you create it, how you read a histogram, how you could create one by hand if you wanted to. It's just kind of a task. The other thing that's really important for us is how to read one. Well, we already started how to read one a little bit, but there's a little more to this. So we're going to look at description of shape. What do I mean by just the shape? The shape has to do with how the rectangles are distributed. I'm going to draw here ones without any numerical values here just to make my life a little simpler, but suppose my histogram look like this. You can notice that this is, somewhere, think about the median again, somewhere's the median, and you can see that this histogram is fairly symmetrical. So if that's the case, this would be symmetrical. Not perfectly symmetrical, mind you, but symmetrical. And like I said, this is just a sample. Maybe the actual population distribution, the parameter, notice sometimes the parameter would be a perfect thing. So the actual shape of the distribution looks like basically a massive rectangle like this, perfectly symmetrical. The data here came from a distribution that might look something like that. Or here's another one that's symmetrical as well. And this is the one that we're going to look pretty closely at as the course progresses. But then we can see there's some, not perfect, but there's some symmetry here as well. And maybe the distribution this one comes from, the data has to come from somewhere. Maybe it looks something like this. So that's where the population distribution looks like. So this, if it's, you can kind of draw the median, and then on either side of the median is pretty much this, symmetrical, then this would be, again, described as symmetrical. So that's one shape description. What's another one? Well, let's draw another one here. Suppose it looks something like this. And again, different shapes, different things. But now I see that it starts out big, and as I progress to the right, notice this is, I'm going to put numbers here just so we can see I'm increasing as I go from left to right. And as I go from left to right, the frequency of the data starts to diminish. I start out big and go out small. So if that's like this, then this would be considered right skew. Sometimes people make the mistake in that they think that they should be looking at the bulk of the information. So that we label this as well, the bulk's on the left side. Like, again, think about the median. It's hard to figure out what the median is here. But the bulk is to the left, and they go, oh, that's a left skew. Nope. What we're interested in is the unusual value. So notice here, as they go to the right, they become unusual. Because what does a histogram do? It gives us, again, a representation of the groupings. And I can see that as the frequency is going down, as I go to the right, it becomes more and more unusual to see numbers in this range. Really, the skewedness means that my unusual values are to the right, which means that if my graph looks something like this, slightly different version. That's this. Something like this looks too perfect. This would be considered now left skew. And again, I'm going to put the same numbers here, 0 and 50. But notice now, as I go towards the smaller numbers, again, reading from left to right, the unusual values are to the left. And of course, these are just samples from the actual distribution. Maybe the distribution that this comes from looks something like this. And you notice we use these shapes without any division to describe the population. So these will be, again, population shapes, which are perfect. And also numerical, again, these are numbers at the bottom here, describing the possibilities. So notice again, these are distributions. And what I mentioned earlier, that what is a distribution? A distribution has two parts to it. What's a distribution? A distribution shows possible outcomes. Okay. And the chance of those outcomes. Sorry. Here now, I don't have, let me look at this one that has actually some numbers in it. Let me go 1, 2, 3, 4, 5, 6. Also, once you describe another thing you have to keep in mind, once you say, I'm going to make my class width 10, it must be true throughout. You cannot change your class width for, within the same histogram. And why is that? Because visually we're attracted to the area. If you change the area, so the interval right here, like here you make it 20, but here you make it 10. But the shape, also the area shape that you're about to create, will not visually match the actual count right here. It will create a different feeling. This is kind of an important aspect of making sure your graph is not skewing the reader's visual information, right? So we got to be a little careful here. So how to determine the chance? Well, here again, I can notice that the numbers at the bottom, whatever they happen to be, I'm guessing here, 5, 10, 15, 20, 25, yeah, so there's something else, maybe 10, 20, 30, 40, yeah. Okay, I didn't do this well. So let's say it's 10, even though that doesn't add up correctly. I can see that between 0 and 10 is not very likely, but let's say this is 40. Between 40 and 50, oh, pretty likely, and between 30 and 40, also pretty likely. So the distribution shows the possible outcomes. Yes, you can get between 30 and 40. And the chance of those outcomes, meaning, well, yes, between 30 and 40, there's a good chance I'm going to get a number in that region. Well, it is possible to get a number between 0 and 10, but not as usual. Okay, so that's what a distribution does. One last shape. So you have your symmetrical, your right skew, your left skew, and then you have shapes that are something like this. So I'm going to draw kind of a nice, perfect one. So you notice that as I go from left to right, it starts to rise, and then it dips down again, and then it starts to rise again. So when that happens, this is going to be known as bimodal. Okay. We haven't talked about this as a measure of center, but there's another type of description for center called the mode. And what is the mode? The mode is the most frequently occurring, like if you were in elementary school, it would be told to you that this is the most frequently occurring number. But data doesn't repeat itself that often, especially if it's continuous. So that's kind of a simplistic description of modal. Sometimes a better description that's a little more, by separating the data into ranges and then counting the ranges, we would say, hey, look, the mode is the most frequently occurring range. So in this case, the mode for this distribution between 50 and 60, like really describing a mode. So what's happening here, if I look at it from that perspective, there's just two modes. One, this range is pretty high occurring, but so is this one. And notice there's two things going on here. So this becomes bimodal. Another way of thinking about mode is mountains. When I look at this, I see one mountain, one mountain. When I see these, I see one mountain, like a mesa, Arizona. So, the mountains that are flat. Here I see one mountain, one mountain, one mountain. But here, I'm starting to see, wait a minute, there's two mountains going on here. So it has to do with the valley. Is there a big enough valley relative to the heights here to account for it? But there's more to it than that. What a bimodal distribution might tell us is that we are merging two different sets of data. Like, for example, what if I merged, have elementary school, and I measure the heights, but I don't grab everybody. I'm going to measure the fifth graders, and I'm going to measure the kindergartens. What would you think would happen? Then, well, the kindergarten class would be here, and then as we move across, the fifth grade class would be here, because really these are two different groups. They're related by age. And of course, it might be a really tall kindergarten kid or a very short fifth grader, and they sort of meet somewhere. So when we see something that's bimodal, we wonder, okay, we really have two different data sets. Here's another one that's bimodal, the Old Faithful in Yellowstone, the geyser. The way there's the eruption time, it's like how long before the next eruption happens. Is it 10 minutes before the next eruption, 7 minutes? It turns out that for the Old Faithful, it's bimodal. Sometimes it happens very quickly, and sometimes it happens, it takes much longer, like 40 minutes, 50 minutes, like an hour. But when you look at all the times it takes for the next eruption, it's forms a bimodal. And then if you start working to figure out why this is happening, it's because there's two, my understanding, very simplistic, there's two different pipes systems for Old Faithful. One that takes a little more to heat up, like there's two furnaces driving the geyser. The one that erupts quicker is smaller, but the one that erupts much higher, well, it takes a while for that thing to heat up. So there's two different pipes leading to the eruption, and that's what's creating a bimodal type of graph. This one's called bimodal, and if you had three shapes, that would be trimodal, and so on. But this one only has one, right? One mountain, one mountain. So often then what we say is that this is unimodal. So this would be symmetrical unimodal, symmetrical unimodal. And this is right skew, but again, one mountain, so unimodal. This would be left skew, but unimodal. Okay, but this would be bimodal. And that's really it. That sort of kind of describes the shapes, histogram distribution. There's other graphs called dot plots, which literally just is a bunch of dots. But again, we can use those descriptions, left skew, right skew, symmetry to describe the shape. There's another type of graph, which we're not going to go into, called the stem and leaf plot. Again, you can use these same descriptors for those graphs. Basically, a histogram is for quantitative numerical data, and so is a dot plot, and so is this other thing called the stem and leaf plot.